Lecture 6. In this lecture, we will deal with one of the fascinating ideas in all of the mathematics, continuity. Before giving a technical definition of continuity, let's briefly give the informal discussion for the concept in order to understand the intuition of the continuity. The informal definition is following. Suppose we have some function f and it has the value fp at some point p. Then we say that f is continuous at p if at every nearby point x, point x, the value of a function fx is close to fp. In other words, if we move x toward p, we want the corresponding function values fx to become arbitrarily close to fp, regardless how x approaches to p. The intuition is following that we do not want sudden jumps in the values of a continuous function. What we don't want is, this is our function, we don't want that to have this kind of jumps. In this case, if we approach to x, then you see the function fp has jumps. The idea of continuity is we don't want our function to behave this way. Let's consider the function, let's say x minus, this is a floor function. If you graph it, you will see it has the following graph. So it goes from 0 to 1 and suddenly jumps to 0 again, to 1, and it again goes to 1 and jumps to 0 and jumps to 0. That is, for each integer we have a jump discontinuity. For example, let's say f1 is 0, but if we approach to 1 from the left side, you see that the function here approaches to 1. However, if we approach 1 from the right side, from this side, you can see that in this case actually function does approaches to 0. In a case like this, the function is called continuous from the right at 1 and discontinuous from the left at 1. To have continuity, it is required to have both continuity from the left and from the right. Now let's understand the concept, what we mean by function approach to some value. Mathematically, we can write this: limit of x goes to p fx equals some limit L. So the limit here is has the similar definition of sequence limit that we covered. That is fx gets arbitrarily close to L as x is chosen closer and closer to p. In this case, the thing you may note that we are not interested on the case where x is equal p. Now let's define what we mean by functional limit. Definition is following. Suppose we have some function which has domain E and codomain R, and we write that limit of x goes to p fx is equal L if for all epsilon greater than 0 there exists some delta greater than 0, such that whenever the distance of x and p is less than delta, it follows that fx is distance between fx and the limit point is less than epsilon. The thing is that this condition is the same as, let's say, delta neighborhood of x, or we can say x is in p minus delta, p plus delta. So we covered the meaning of the neighborhood. To graphically interpret the point, suppose this is our function f, then what we mean by saying that so this is point x and those are x minus delta and x plus delta. And we say that if for points that are between x minus delta and x plus delta, then the functions should be, the distance between function and L should be epsilon. Now let's do a couple of examples that illustrate this definition. We want to prove that fx is equal, if fx is equal to 3x plus 1, then limit of when x goes to 2, fx is equal to 7. We just directly use the definition. Suppose epsilon is greater than 0, and what is required, we need to produce delta greater than 0 such that x minus 2 less than delta. And we need to end up having a conclusion that fx minus 7 is less than epsilon. Let's directly apply this. So we have fx minus 7 is equal 3x plus 1 minus 7, which is equal 3 times x minus 2. Now if we choose delta is equal epsilon over 3, then we have that for x minus 2 delta, fx minus 7 is less than 3 times epsilon over 3, which is equal epsilon. And we prove that the limit of fx when x goes to 2 is 7. As long as we understand the functional limit, we are ready to define the concept of continuity. We start by defining continuity at a point. Function f from E to R is continuous at a point if for all epsilon greater than 0 we can find a delta, positive delta, such that whenever x minus p is less than delta, we have that fx minus fp is less than epsilon. So to prove continuity, the procedure is following. You give me epsilon, any epsilon you want. So my job is to find a delta such that the difference of the points in the domain is less than this delta. And I need to conclude that the function itself for these 2 points the difference of this function is less than epsilon. If we can prove that, then we are saying that there are no jumps. If f is continuous at every point, if every point in the domain then we say that f is continuous on E. The thing you may observe is that function f failed to be continuous at a point P in three ways. First, f is not defined at P. Second, limit of fails to exist. And the third point is that f is defined at P. As well, the limit exists, but the limit does not equal to fp. Let's do one more example. Suppose we have function from 0 to infinity to r, and the function defined fx over 1 over x. We want to show that f is continuous at P. F is continuous at P, which is in 0 to infinity. To understand the intuition, let's first of all draw this function. From this plot, it's obvious that the function is continuous, but we need to give a rigorous mathematical proof. To prove it, again, we take epsilon greater than 0, and we say that xp is less than sigma. From here, our job is to prove that 1 minus xp is less than epsilon. This is equal p minus x over xp, but we know that xp is always positive, so this is times p minus x. Now if we take delta as xp times epsilon, then we have that p minus x is less than epsilon times xp. So from here is equal 1 xp times p minus x, which is equal xp over xp, and we have, so this is less than. So therefore we prove that the function is continuous. Now let's talk about some properties of continuous function. We start by defining a theorem. Suppose we have two functions fg which are defined from E to R, and we have some constant C in R, and suppose f and g are continuous at a point P. Then we have that C times f plus g, f times g are continuous at point P. And if function g at point P is not 0, then f over g is continuous at P. We are not going to prove these properties, but they are not difficult to prove. Instead, we will do example, and which says that every polynomial is continuous on R. To see the intuition of this example is polynomials can be, let's say, polynomial of degree 3. We can represent as the following way, plus some constant, let's say. Suppose this is our function. Then, using only theorem above, we can say that since x is continuous, then x times x equal x cubed is continuous. And the same way, 2 times x squared and 6x continuous, and also the constant is also continuous. Then, using the property 2, we can conclude that the sum of continuous function is also continuous. Therefore, fx is continuous. The other interesting property of the continuous function is related to the composite function. So the theorem says if we have function f and g such that f goes from a to r and g goes from b to r, such that the range of the function f is in R. If f is continuous at a point P in A and G is continuous at point Y, which is Fp, and belongs to B, then the composite function is continuous at P. Let's do very interesting example, which you may also see in your Econ 629 class. Suppose we have function defined as following. It's 2x if x is less than 3, 2x plus 4 if x is in 3 to 6, and 2x plus 6 if x greater than equal 6. And the domain of function x is from 0 to infinity. Now the question is, obviously this is a discontinuous function. To plot this, the function is following. It goes from 0 to 3, then it has jump from 3 to then it goes to 3 to 6, and then from 6. So now the question is, can we fix the discontinuous function and define new function based on this discontinuous function such that it is continuous? Basically, what we are trying to do, we are trying to fix the jumps. If you look on this plot, you may notice that if we were able to kind of increase this part from 0 to 3, so move it up such that our new function is here, And what else we need to do? We need to move down the part from 6 to 10. As long as we do this, we'll have continuous function by fixing the old function. To do this, we may define new function g, and we say that gx is equal fx plus 4. Since the difference here is 4. Yeah, I'm not a good drawer, but you get the point. For x less than 3. Then we define that gx is equal fx itself for x from 3 to 6, and gx is equal fx minus 6 for x greater than equal, so for x 6 to infinity. Since the difference here is 6, so what we did, we fix our function fx and introduce new function g, which is continuous in domain of fx. You can notice that gx is composite function. So we define a composite function based on discontinuous function and fix discontinuity. The next topic we will cover is continuous functions on compact sets. We start with definition. We say that function f from a to r, if we have function f, then f is bounded if we can find some m which belongs to positive part of real line such that fx is less than equal m for all x in A. Let's do a couple of more examples to understand what we mean by bounded. Suppose we have function f from A to R. The function f is defined by fx is equal 1 over x squared. Let's suppose our domain is from 0 to infinity. And the thing you notice here is that f is unbounded, since when x goes to 0, fx goes to infinity, therefore there is no m such that fx greater than equal m. Since near 0 the functions start to behave very bad. But if we move a little bit farther from 0, let's say by 0.5, then for this part f is bounded, since we always can find a m such that fx is bounded. Recall that we say that the set is compact if it's closed and bounded. Now the theorem says that f is continuous and k is a subset of A is compact, then fk is also compact. If we combine this theorem with the observation that compact sets are bounded and contains their supremum and infimum, then we get a very famous theorem of extreme value theorem. Extreme value theorem says if function f is continuous on compact set K in R, then f attains a maximum and minimum value. That is, if we have function over the compact set, then maximum and minimum always exist. In other words, we can always find x0, x1 in K such that fx0 less than equal fx less than equal fx1 for all x in K. This is very important and useful theorem. You will use this theorem all over your PhD course. The other observation is that continuous function on a compact interval obtains every value that falls between the range of the boundaries of the interval. In other words, if we have function f which goes from ab to r, where ab is a closed, and the f is continuous, and we have L real number such that fa is less than L and less than fb, or fa is greater than L and greater than fb, then there exists a point in the interval where fc is equal L. This is called intermediate value theorem, and graphically suppose we have some function so this is B and this is A. So what the theorem says, there exists always C such that L is equal FC. The proof of this theorem uses something which is called Rhodes theorem. So we are not going to prove it in this class.